Welcome back. What we're going to do in this session is talk about networking models, and this is objective 1.1. I'll try to do this, which is compare and contrast the OSI and the TCP/IP model. What these models allow us to do is to standardize equipments. If any of you have been around for quite a while in the networking world, you may remember when if you wanted to add a network interface card, a NIC, to your computer and you had a Dell, you had to go buy a Dell NIC. What modeling allows is for standardization so that we can now have competition, for instance, in the world that we live in for the different devices. And the world that we live in, I always think about it, is in computers, and the IBM PC brings the price down because there are multiple vendors. And that's what modeling is going to allow us to do. What it also permits is the ability to assist us in troubleshooting, so that if something fails, we don't just have to throw up our hands and say, I have no clue what it is. We have an idea where to start. It's kind of like building something or manufacturing. What I was thinking about is manufacturing a car or building a computer or whatever. Each individual has their job in an assembly line in order to make the final product. And that's what's going to happen in these models. They have been around for a long time. OSI, Open Systems Interconnect, and the TCP/IP model, one that originally was called the DoD model, and it was actually built to support the TCP/IP protocols, which are the ones that we use today. So when we do these things, why use models? Why models? It reduces the complexity of large problems to 7 smaller ones. If we're not connecting, let's say, to an IP address, then we know what to troubleshoot. If we can't display a particular type of file, a doc file, an HTML file, then we know where to start our troubleshooting, so that it does assist us, and it is important to know about it from a networking, from maintaining your networking, and then even in a security standpoint. How can we filter different things? How can we allow specific connections and disallow other connections? So in each of those items, it allows us to reduce the complexity, reduce our objective from, oh golly, we have this monumental task to, okay, what layer of the model is this problem or is this issue that we're having, so that we can then go in and work on that particular layer or that particular aspect of networking. Allows for the standardization of interfaces among devices, and this goes back to what I said earlier, so that if we have a Dell, an AST, a Compaq, or whatever else, we don't have to go buy a device that was manufactured by by that vendor. We can go to the store and buy a NIC that works on whatever our particular bus arrangement is in our machine, and then we install the driver that interfaces it with the operating system that we're using. Prevents changes in one layer from affecting other layers, and I guess the biggest example of that right now is IP going from IPv4 to IPv6. When we do that, the only thing that has to change is the layer that operates with the IP protocol, so that we can now have a smooth transition from one protocol, IPv4, which, as we know, is limited, to IPv6, which has more addresses than we think that we're going to use at this time. Of course, when the IPv4 originated, we thought it was going to be the unlimited addresses at that time too. So prevents one layer from affecting all the other layers. We can change one aspect of it. Allows engineers to concentrate on specific design of functions in each layer, so that we can optimize, the engineers for the IP can optimize the IP layer engineers that are going to work on application programming interfaces can optimize those particular aspects. The lower 4 layers, I'm going to have an image here in a second, of the OSI model are concerned with shipping the data, getting the information from point A to point B, and that's what we're concerned with in our routing and switching management, so that we do that. The upper layers deal with applications running on end devices. We're predominantly talking about computers here, the end devices, so that we can connect one station to another station. And when we go to a website, we're obviously connecting to a computer running an application, a web server application at the other end. Multi-vendor interoperability, creating products to meet the same networking standards, means computers and networking gear from multiple vendors can work in the same network. We can have, they're configured differently, obviously, different commands, but we can have a 3COM router and a Cisco router in the same network, and they use standard protocols so they can each handle the data that we're trying to ship. And back to the four lower layers of the OSI model concerned with shipping data, and that's what we're concerned with, so that we can have different vendors in our network. And some security specialists recommend that, so that if one particular manufacturer's devices is compromised, everything's not compromised in the same manner. Modular engineering, one vendor can write software that implements higher layers, for example, a web browser, and another can write software that implements the lower layers, for example, Microsoft's TCP/IP software in its operating system. So different vendors, different aspects, and they all work together because of modeling. The image here that we're talking about, these are the layers of the OSI model, the application, and we're going to go through each of these individually. Presentation, session, and the applications on the end devices. Up here, the top 3 layers. The bottom 4 layers, transport network, data link, and physical, are the data shipping. Those are the ones that we're going to be concerned with in our routers and switches. Mnemonic on how to remember these things from the top to the bottom. All people seem to need data processing, which is the first letter of each of these things. This is one that I've never personally, I do now, but it took me a long time to memorize it, and I don't know why. I just had a block. But the one that I could remember was from layer 1, the physical layer up, which is please do not throw sausage pizza away. And again, the first letter of each of the words in the mnemonic represents the first letter in each name of the layers. And they go from the bottom 1, 2, 3, 4, 5, 6, 7. The bottom physical layer 1 to the top present application layer 7. So different looks at it, what it is, what the names are in this thing. This is just a different image OSI model which represents what we are going to go through in words here in just in the next few minutes. But down here in layer 1, which is the physical layer here, layer 1, we have the media, signal, binary transmissions, and these are the protocols that are going to be involved here. RS-232, which is serial, RJ45, the connector that we use for twisted pair, 100 base TX, which is going to be 100 megabit per second twisted pair cable, SDH, DSL 802.11, different protocols, and then kind of some images of what goes on there. Layer 2, the Datalink layer, we have physical addressing, and we have 2 different types of addressing. Physical addressing, which is also called the MAC address, media access control. The protocols that are here, Ethernet, 802.11, and we're going to talk about all of these things, just introducing the terms here. MAC, LLC, ATM, fiber channel, frame relay, HDLC, protocols that are going to be running at layer 2 here at this layer. Next up, network layer, the protocols IP, ARP, IPsec, ICMP, ping, OSPF, different routing protocols that are available there. Path determination, logical addressing. Layer 3 is IP addresses. IP addresses can and do change. The MAC address down here, the physical addressing, is permanent. So we have a permanent MAC address and an ephemeral or a temporary IP address that's assigned to these things. And then layer 4, the transport layer, TCP, UDP, and those are going to be the topic of the next objective, compare TCP and UDP, the way that they work. It's responsible for end-to-end connections and reliability. And reliability is going to be a big deal here when we talk about TCP. So we have the transport layer, the session layer, layer 5, session establishment, and TCP, SIP, RTP, different protocols to do those. So it's responsible for inter-host communication. It controls which device can talk at any given time. And then the presentation layer, data representation and encryption, recognizing the data HTML doc, the type of document that we have, to be sure that the application layer, the layer 7, network processed application. When we talk about application, we're not talking about Office. That is not the application that we're talking about here. We're talking about things like a web server, www, HTTP, DNS, domain name service. So services run here, an email server would be the things that would operate here. And this presentation layer is responsible to be sure that the data presented to the application layer can be read. So each layer of the OSI model is responsible for supporting the layer above it. And when we go up, when we go down, we're actually going to start on the device over here. The computer's out here somewhere. The computer connects to this thing. It's not part of this process. This is the process to get data from point A to point B, to go from one place to the other. So we'll start out, we'll connect with this thing, with the computer, and it's going to go down the OSI stack. We're going to start out with, we're going to maybe go to a web page, we'll do a web query, we'll go down the stack, and we'll do encapsulation, where each of the layers adds its header until we get down to the physical layer, and then it translates it into ones and zeros for transmission across the devices. So look at that, and then maybe to reinforce some of this, we go into the physical layer, a little bit wordier, I guess, representation of what goes on here. Defines the electrical and physical specifications. What kind of voltages do we have? What kind of signals are we going to use in this thing? And part of what has increased our speed as we've gone across the years from, like, you know, in Ethernet from 1 megabit per second to now we're up to 10 gigabits per second, 100 gigabits per second, is compression in the way that the electrical and physical specifications play out in it. A relationship between device and physical transmission medium. For example, an electrical cable, optical fiber cable, or radio frequency. Are we going to use electrical cable? We're going to use copper, or we're going to use fiber, or we're going to use wireless. Includes a layout of pins, voltages, line impedance, cable specifications, signal timing for connected devices and frequencies. 5 gigahertz, 2.4 gigahertz, the two wireless standards that we use. Generally speaking, the lower the frequency, the greater the distance. The higher the frequency, the shorter the distance, but the higher the data rate. So we can get more data across the higher frequency ones. Responsible for transmission and reception to unstructured raw data in a physical medium, and that's where we just translate everything, we turn everything into ones and zeros and send it out on the media itself. Bit rate control is done at the physical layer. May define the transmission mode as simplex, half duplex, or full duplex. Broadcast mode, simplex is broadcast. Simplex is one-way communication. so that we broadcast much like a radio station, for instance, or a television station. Half duplex means that we can transmit and receive, but we can only do one at a time. So we can transmit, we can receive, but we can only do one of these at a time. And what I kind of like to think about that is we have this big highway here perhaps, and we go down to a one-lane bridge, which only allows us to go in one direction at a time. So we can transmit, we can receive, and we can only do one at a time. Full duplex is like an interstate highway. We have lanes going in each direction, so that, and part of it is so that we don't have collisions. If we have this situation here, we can certainly have collisions, and we do have collisions in half duplex. In full duplex, transmit and receive at the same time, then we don't have collisions. And what that means is that we have 100 megabit per second connection. We have 100 transmit and 100 receive, which really gives us a 200 meg connection when we do these things. Physical layer is the layer of low-level networking equipment such as hubs, cabling, and repeaters. And what a repeater does is just repeats the signal. It's not an amplifier. If it amplified, it would amplify the noise. So what happens in the physical layer is we start out with a signal and it degrades over time. What we have to do is restrict the distance that it can go so that the noise level down here, the electromagnetic interference, doesn't overcome the signal. So at this point, we would repeat it. Since it's ones and zeros, it's easy to pick out the ones and zeros and distinguish it from the noise and regenerate the signal and start over again when we do these things. It's never concerned with protocols at the higher levels. Examples of hardware in this layer are the network adapters, repeaters, hubs, modems, and fiber media converters. So physical layer concerned with the ones and the zeros, getting it from point A to point B, connecting point A and point B together. The Datalink Layer, node-to-node transfer, node-to-node, device-to-device, computer-to-computer, computer-to-router, router-to-router arrangements here. Between two directly connected nodes, detects and possibly corrects errors that may occur at the physical layer. It's really unlikely that a whole lot of correction is going to take place here. We can, depending on the type of switch that we use, we may reject error-laden frames as they go through switches, and we'll talk about that a little more later. Detects, possibly corrects, defines the protocol to establish and terminate a connection between two physically connected devices. It also defines the protocol for flow control between them. IEEE 802 divides the network into two sublayers, the media access control and logical link control. What does all of that mean? Media access control in true Ethernet, go back to the very first one, we had this piece of cable here, coax, that we connected everything to, so that if station A transmits to station D down here, it puts its signal, let me see if I can get a different color here, puts its signal on the wire to go from location to location. If at the same time B tries to go to C and we put its signal on the wire, then we have a collision. When we have a collision here, we have to start both conversations over, much like if you're in a room and a lot of people try to ask a question at the same time. Nobody understands what's being said on any of these things. So what the MAC layer does for controlling how devices in the network gain access to the medium and permission to transmit the data, we have this thing called CSMA CD, Carrier Sense Multiple Access Collision Detection. So what the devices do is carrier sense, there's a carrier signal on here that runs at a particular frequency. So it senses the carrier. Multiple access, obviously, because all of them are connected to the same piece of wire. They have to share the same piece of wire in that collision detection. So a machine listens to the wire to see if there is a signal on it. If there isn't a signal on it, then it sends its transmission, puts its transmission on the wire. The other station here is listening, and it should hear this transmission on the wire, and then it's going to wait for access to the media until this conversation is done. Once this conversation is done, then it can do the same thing. If two of them transmit at the same time and we have a collision, then we do a random back off. Random back off. And start all over with the listening and the waiting and doing all of those other things. The logical link control LLC layer, identifying and encapsulating network layer protocols and controls error checking. So you notice that the network layer is above here. So what it does, and we really, at this point in time, we're only using one network protocol, which is IP. Actually, we're using two now, right? IPv4 and IPv6. So what you think about it as a protocol, a conduit from the data link layer to the network layer. So it sends it to the proper network, sends it as the proper network layer protocol. The MAC and LLC layers of the 802 networks, 802.3 Ethernet, 802.11 Wi-Fi, 15.4 Zigbee operate at the data link layer. The point-to-point protocol is a data link layer protocol that can operate over several different physical layers such as synchronous and asynchronous serial lines. It's going to be a serial protocol. So we're going to have, and this is at the data link layer, we're going to have local area networks, LAN with LAN protocols, Ethernet being the one that we use, fast Ethernet actually anymore. Ethernet, and then we're going to have WANs, which go long distances, and we're going to have protocols such as point-to-point protocol. Cisco proprietary is going to be HDLC, which is going to be the default on all the Cisco devices. So 802.11 or 802.3 for wired and 802.11 for wireless transmissions across using these devices. So the next is the network layer. We still have some others to go. As we get on up in the layers, they become less stringent, I guess. Fewer things happen. But we're a little over 20 minutes, and I said I was going to try to limit these things to about 20 minutes, 20 to 30 minutes at a time. So what I want to do here is to stop this one and then pick up the second half of the OSI model and then the TCP/IP model in the next session. So we'll see you there.